Hi everyone, welcome to another remote session of Math 273 Statistical Models. Today we're going to be continuing with talking about multiple linear regression and picking up where we left off last time, which was on nested F-tests. So picking right up there, last time we began talking about a nested F-test and how we've actually seen them before. We just didn't call it a nested F-test. So the overall F-test, which allows us to test the statistical significance of our whole model, is actually a nested F-test where we're comparing two models, the current model that we're considering and then a model with just only an intercept. We're seeing if those two models are different. And the idea is that if we have a more complicated model, a model with more predictors, versus a simpler model, a model with less predictors, if they perform not that different, we want to take the simpler model because in general, those will have better predictive power in the future for unseen data. So going into more detail about this nested F-test, specifically we have this larger model that we're considering, which is commonly referred to as the full model that has, say, k number of predictors in it. And we're comparing it to a reduced model, which is a model with the same predictors in it. They have to be the same predictors, but some removed. So just a subset of those k predictors in the full model. It's important that they have to be a subset so that the model is sort of nested in the other model. That's where the name comes from, nested F-test. And to calculate that F-test statistic, to compare if these models are statistically different or not, we use this formula here, which is given in the textbook. So we have the sum of squares model for the full model, the big model, minus the SS model for the reduced or smaller model, and then divided by the number of predictors that we're testing. So for example, here we have that we're trying to remove. So if the small model has 3 less predictors than the full model, then this number of predictors tested is 3. So it's the difference in the number of predictors between the models. Then in the denominator, we have the sum of squared errors for the full model divided by n, which is the number of data points in our data set, minus k, the number of predictors in the full model, minus 1. And so this follows in F distribution, which again, if you take like a statistical theory class, you'll get more familiar with like what an F distribution is. If you've heard of like a chi-squared distribution, it has to do with a ratio of 2 chi-squared random variables. And so this follows an F distribution here with a numerator degrees of freedom that is again, the number of predictors less in the smaller model, in the reduced model, and the denominator degrees of freedom is just n minus k minus 1. So kind of an ugly test statistic, but often you'll use software to get this value, or R. So again, as I was just mentioning, this is a generalization of the overall F-test, the test of our model as a whole that we've seen previously. So we've actually already used nested F-tests, where just the smaller model is just a intercept-only model. So let's look at an example using the NHANES data set. We're going to consider 4 models actually here. And notice how they're all nested in each other. So we can use this nested F-test. So we're going to have systolic blood pressure as per usual that we're modeling as our response, an intercept. And then our first predictor is going to be the age in years of the person, X1, and then X2 is going to be their heart rate. And we're going to consider a model with just age, model 1, model with age and heart rate, model 2, an interaction model, and then a full quadratic model, where we have the interaction between X1 and X2, and then each of X1 and X2 squared. So this, the fourth model, for example, has 1, 2, 3, 4, 5 predictors in it, because we view these newly constructed ones as sort of new predictors. So in real life, you would have this decision before you to decide, oh, which of these 4 models should we use? And it's certainly not the case that we should always use the most complicated model, the one with the most terms. That's definitely not the best thing to do in general. We'll always be able to increase our R squared by including more terms in our equation like this. But again, this leads to overfitting of the data, which is bad because we're not actually explaining a true relationship that's there. We're just capturing noise in the data. And by doing so, our model will actually perform poorly for future data, or unseen data that's not in our current data set, which is not ideal, not what we want. So we want to have this trade-off between like important predictors in our model, but not having too many. So we fit each of these 4 models using R. And again, so I have this first model, the simplest one with just age, then age and heart rate. Then I add their interaction term on here using the capital I inhibit function in R, where I'm actually just multiplying age and heart rate. That's the interaction between them. And then the same for model 4, but also with the quadratic terms for age and heart rate. And what I did with the code up here is prior to fitting these regression models here, I just removed missing values in the data because there's actually a lot of missing values in the NHANES data set. So using this complete.cases function, I'm essentially just removing missing values. All right. And then after we fit each of those 4 models and store them in these R objects called mod 1 through mod 4, we can compare them using a nested Ftest by using this ANOVA function, which stands for analysis of variance. And so we just give them as arguments to this ANOVA function, and it'll produce this output that'll look something like this below. And so here, this column is the residual degrees of freedom. We're not going to be too concerned about that. And the residual sum of squares, and then the model degrees of freedom, sum of squares, model, I believe. And then what we care about here, what's most important that we're caring about, is this column that's saying probability greater than F. This is our p-value column. Okay, and the ANOVA function here is important or particular in terms of what order you give the model objects here. So by giving them in this order, model 1, model 2, model 3, model 4, it's comparing model 1 to model 2. That's given in the second row here. Model 2 to model 3, that's in the third row here. And model 3 to model 4. So it only compares essentially consecutive model fits given to it here. You can only compare 2 models at a time with this nested Ftest. And these NAs, by the way, in the table stand for not applicable, or this is how R represents missing values. And so these are in the first row because there's nothing to compare model 1 to. So it is just has missing values here. So long story short, looking at the p-value column here, we can see that the first p-value for comparing model 2 to model 1 is 0.0385. So this is indicating that model 2 is statistically significantly different than model 1 in terms of how well it's fitting the data. In other words, model 2 is explaining a significant amount more of the data than model 1. So even though it's a more complicated model, it has an additional predictor in it, it's saying it's different enough, it's doing a good enough job that we should include that model because this p-value is less than 0.05. Model 3, however, has a p-value of 0.1803, so this is indicating that Model 3 is not that different than Model 2 because the p-value is greater than 0.05. So this would suggest we should go with Model 2 over Model 3 because Model 2 is simpler. So again, because the p-value is larger than 0.05 here in the third row, this corresponds to Model 3 being not considered different than Model 2. So we'll select Model 2 based on that, choosing between Model 2 and Model 3 because its p-value is large. So there's a lot going on here, but hopefully this makes sense in terms of which model this table is implying we should select. One thing that is a little bit tricky here is that Model 4 has a p-value that's very, very small. Now, this does not mean that this is the best out of all the models here in the ANOVA function considered, but this is telling us that Model 4 is doing a much, much better job than Model 3 in explaining the response variable here. So in short, we've learned that we should pick Model 2 over Model 1, we should pick Model 2 over Model 3, and we should pick Model 4 over Model 3. But we haven't learned if we should pick Model 2 over Model 4 or 4 over 2. We haven't directly compared those because this ANOVA function only compares adjacent models here in the function. But we can just run this code again, where we just have Model 2 and Model 4. So sort of just what I was talking about here. It compares the models in the order specified, and there's a number of different pairwise model comparisons that went on there. So again, just by only giving it Model 2 and Model 4 into the ANOVA function, we can then compare these two models. And so here we see 4e minus 0.4, so this is standing for, R likes to use this scientific notation, but 4e minus 0.4 is just another way to write 0.3 zeros and then a 4. So another p-value that's very, very, very small. So this is indicating that Model 4 is doing a much better job than Model 2 in explaining the data. So after this whole process of doing the nested F-test, what we have found is that we should use Model 4, which was the full quadratic interaction model, second order model, to best explain our response. So in this case, the nested F-test did tell us to take the most complicated model, and that that's our best one to go with. But that might not always be the case, so that's why we went through the nested F-test to determine that. And I also want to point out that I think the reason it picked this very complicated model, the one with the most predictors, is because in part the data set is so large, because the number of observations is so large. So in general, not always, but generally, the larger your data set, the more complicated model will be favored. And this is because with having more data available, we can capture more complicated or intricate relationships going on in the data. But if you have only, say, 20 data points, it's hard to capture like a cubic sort of or quadratic fit because it's more complicated than just a straight line. It's hard to justify with a smaller amount of data that you have that sort of complicated relationship that you're describing. So moving on from nested F-tests, we can also look at this concept of added variable plots. So these allow us to explore the effect or the importance of a predictor after accounting for another one. And the main idea is to see, is this new explanatory variable important, even though we already have this other explanatory variable currently in our model? And to do that visually, rather than just using some statistics. So we're going to look at an example from the textbook that contains data on housing prices and different factors that can affect those prices. So loading this from the Stat2 data package, this is called houses, and we're modeling price. The selling price of the house is our response, and the lot size in square feet as our first predictor here. And so we're going to plot the residual by fitted plot. And here we see there's actually a little bit of an apparent pattern in the data, so that's a little bit concerning. Not that we're talking about checking regression assumptions right now, but going back to that, typically, again, when you see some sort of pattern, ideally we'd want a random cloud of points around the dotted line at 0 here. We don't want this U shape. That seems to indicate potentially that a predictor was left out of the model, most commonly, or potentially that our assumption of independent errors is violated. One of those two issues is usually what's the culprit for this. So that plot showed the residuals from modeling price using the lot size of the house. And the residuals are sort of representing what we didn't explain with our model, what we didn't explain with lot, in this case, the lot size. So we can separately, suppose we're considering this other explanatory variable, the size of the house. We can also look at the relationship between the size of the house and lot. The idea being if they're very, very much related, if size and lot are very predictive of each other, lot or size probably won't give that much more information about price above that of lot if there's a lot of redundancy in the information they're giving. So looking at, to create an added variable plot, actually what we do is we fit another regression model where we model the new predictor we're considering by the current predictor already in our model. And so here, plotting this relationship with a scatter plot and our line of best fit in blue, we can see that they do explain some of each other, but not perfectly. There's random scatter about the line. So that was not the added variable plot yet. An added variable plot actually is a plot of two sets of residuals, a scatter plot for two sets of residuals. So from that model, from the second model we just fit, we can obtain a different set of residuals, which is representing the error from our line of best fit to the actual points, this distance for each of the points. And we can consider plotting the residual by fitted for these values as well here. Again, we see a bit of a U shape, maybe a little bit, but not as egregious as last time. So the assumptions don't appear violated here for that plot. But anyway, what we're looking at here is plotting the residuals for the first model fit, which was price by lot, and then the second model, which was size by lot. So we get the residuals for each of those models, and then we actually fit a third regression model. So it starts to get a little bit convoluted with added variable plots. But the reason we go through all this is because it's a way to graphically visualize the importance of additional predictors for our model. So anyway, if we create this scatter plot with the residuals from the first model, which is representing what lot did not explain in price, and using the residuals from the second model, which is representing what lot did not explain in size. So what's left over in the size of the house independent of the lot size. And plotting this, we can see there's a little bit of a relationship here, but it's actually very, it's pretty cloudy. There's not a clear trend in this plot here. So that seems to suggest that after accounting for lot size, the size of the house is not that important in terms of predicting price. So again, to reiterate what I just said, so because the pattern of the points is pretty random, there's not a clear linear relationship here, this suggests that the size of the house does not explain much more after the lot size of the house. It gets a little bit confusing with lot size and the size of the house, but I'll say the square footage of the house doesn't explain much after lot size in terms of the house price. And looking at the correlation between these residuals, we see it's 0.303, which is kind of small, not crazy big by any means. So this indicates again that size does not explain a significant amount above what lot already does for price. But if we had a large correlation, a correlation that was big in magnitude between these two residuals, that would suggest we should maybe include the house size as well in our model. So added variable plots can be one way we can decide to include a variable or not in our model. We could also, again, look at the nested Ftest. So the nested Ftest was sort of a way from before that we could do that based on hypothesis testing. Added variable plots was a way we could consider adding new predictors by using graphical displays, by using scatter plots. There are many other ways we can consider or decide how to add or select new predictors for our model as well. So again, going back to what we've seen previously, we can always make new predictors from our current explanatory variables. And so it's always a question of should we do this or not, though. It can always increase our R squared, but again, we don't want to overfit our data. So overfitting specifically is when our model is explaining sort of random noise in the data and doing this well, but as a result, it will have poor predictive power for new data, unseen data that our model has not been used for fitting. So an example I always like to think of this is that I remember I had a friend in undergrad who wanted to predict the scores of college basketball games, and he had a ton of information available that he'd gotten online. He had like 30-something predictors, and he saw that when he fit this huge, gigantic regression model, including all the interaction terms, all the quadratic terms, he got an R squared of 0.9, which is very, very high. He was explaining nearly everything in the response in the college basketball game scores in his data. But then when he used his model to predict for games for the next year, games his model was not fit on, it did very poorly. And I think he said it was even wrong most of the time. It picked the wrong winner based on the score more often than not. So it did a very, very poor job. And this might seem surprising. So like the R squared is really large. So you might think, oh, my model can do great in predicting stuff in the future. But this isn't the case, actually. If we add too much to our model, it can actually start to make it do worse, and actually significantly worse. So one way to visualize that is in this scatter plot here with two different models. We have a red model and a blue model. So the red model is representing a model that's overly complex and is overfitting our data. And we have the points in black, the black circles here. While the blue line is just a simple linear regression model using X to predict Y that is doing a much better job of not overfitting the data, but still explaining a lot of the variability in the data. So for the red model, we can see it goes through all the points exactly. So actually the residuals are all 0 because there's no error in terms of how it's fitting the data. And again, this would yield an R squared of 1. So we'd say 100% of the variability in our response is explained by our model. That's what the red model would yield. But in reality, if we got new data, if we got new data points, they'd probably fall, randomly in this way. In which case, our blue line is doing a much better job than, and maybe I'll say the new points are in green. Our blue line would be doing a much better job of fitting the new data, the green points here, than the red one. Because, for example, the predicted value for the red here would be way, way off for the green point here, but the blue line is not as much off. So this is the benefit of picking a simpler model, in that for new data, unseen data, we'll tend to get better predictions if we did a good job of deciding on the trade-off between simplicity of our model, having less predictors, but also fitting the data well still. And again, the main idea is we don't want to model just random fluctuations in the data. We want to be capturing that true relationship that's there in the data, not just blips that are happening by chance. And some people refer to this as saying we want to model the signal rather than the noise in the data. And in general, the more complex your models are, in other words, the more explanatory variables you include, the more interaction terms, quadratic terms, the more prone your model is going to be to overfitting. So that's why it's important to know sophisticated ways to choose how many predictors to have in your model, such as the nested Ftest, looking at added variable plots, and a very commonly used measure to assess whether to include more predictors or not in your model is to look at the adjusted R squared. So we've seen this before very briefly, but R squared just measures how well we're explaining our response. And adjusted R squared is sort of an extension of this that also penalizes for having too many predictors in your model. So the more predictors you include in your model, the more adjusted R squared is penalizing for this. But it's still rewarding good fitting the data well. So in this way, the adjusted R squared is useful for selecting a model that is simpler, in other words, has less explanatory variables, but is still doing a good job of explaining our response. And one approach to use this is to sort of work from the ground up, starting with no predictors, adding one, calculating the adjusted R squared, adding a second predictor, calculating the adjusted R squared, and so on. And then you have all these candidate models. All these models you fit, and you have the adjusted R squared for each of them. One way to decide is just pick the one with the biggest adjusted R squared. It's kind of that simple. I'm not saying that's the best approach, but when it comes down to it, just picking the model that has the biggest adjusted R squared is not a bad approach. So that's one method for selecting a model. Another way is to use what's called a best subsets approach. So this is kind of an interesting idea that someone thought of, is that let's say we have 50 predictors total at our disposal, which is a lot of possible predictors to use. But maybe we will only want to use, say, 5 predictors in our final model. And we want to find the best possible model out of all these many explanatory variables that we have. What we can do is literally fit every single regression model that has 5 predictors in it. So take every combination of 5 explanatory variables out of, say, these 50. Fit every one of those regression models, and then pick the one with the biggest adjusted R-squared. So this would be extremely computationally expensive. And this is because when you have a large number of predictors, this grows very quickly in terms of the number of combinations that you can choose. So for example, and they call this like combinatorics. If we had, say, 50 predictors, choose 5. I'm just gonna Google this real quick. 50, choose 5. So this, for example, is equal to 211,8760. 8760. So if we had just 50 predictors possible and we wanted to just pick 5, then by doing best subsets approach, where we fit every possible regression model with 5 predictors from the 50, that would be over 2 million regression models we would have to fit. That's a crazy number. So even though computers are very fast these days and getting faster and faster all the time, it's still extremely computationally expensive to calculate or to fit 2 million regression models, even for like a supercomputer, maybe not, but for us run-of-the-mill everyday data analysts, we don't really have that option. So this is only really feasible if you had, say, maybe 10 predictors or even like 15 predictors, a smaller number of candidate ones that you're trying to choose from. But as you can see, it gets out of hand really quickly. So another metric, another measure that we can use to select a model when we have all these candidate ones we're considering is called MOLO CP. And so this was named after someone whose last name was MOLO, I think. Kind of sounds like marshmallow, which is kind of funny. It's kind of similar to the adjusted R-squared, similar in spirit at least. So it's calculated as SSEM, where M is just a model with only M predictors in it. And we have this full model that we're considering, and we calculate the MSE for that full model, which has K, which is bigger than M number of predictors in it. And then we add to that. So this is the part that's representing how well the smaller model with only M predictors is fitting the data. This part's representing that quantity. And we want to minimize it. We want to minimize the SSE in general for our model. So we want this to be smaller if we want our model to fit better. And this part, 2 times M plus 1, M is the number of predictors in this smaller model. So this is the penalty for complexity. In other words, it's penalizing for the number of predictors, M, in this candidate model. And then for some reason, the MOLO CP subtracts N, the number of data points, observations in our data set. N is the same for all candidate models here. So I think it has to do with other theoretical reasons why they subtract away this N. But the main takeaway from this equation is that this part's representing how well our model's fitting the data, and this part assesses the complexity of our model, how complicated it is, how many predictors it has. So in general, you can think about, would we want MOLO CP overall to be minimized or maximized? So I'll let you think about that for a second before I answer it. So in general, we want to minimize MOLO CP because we want to minimize SSE and we want to have a smaller model when possible, minimize the number of predictors in our model. So again, to reiterate, in general, we want the largest adjusted R-squared for a model, and then we want the smallest MOLO CP. So those are two metrics, two statistics we can use to select a model based on a set of candidate models that we have at our disposal. Next video, we're going to talk about even more methods that are used for selecting models. I think this is one of the most important concepts, so that's why I'm sort of flushing it out here and going over it a lot, because I feel like for data analysts in the real world, you always have a lot of data at your disposal nowadays. So one of the biggest skills is going to be data cleaning, preparing that data for analysis, which we don't go over in this course, but in this course, we're learning how do we properly model the data once we have it ready for analysis. And so with that comes the decision of selecting which predictors to include. So this is always a big decision to make. And again, there's not one right answer. There's a lot of different ways to go about it. So we're just reviewing some of the ways, going over some of the ways you can do that. So again, next class, we'll continue talking about more ways we can select which regression model we want to use. So thanks, and I'll see you guys then.